Thank you. So, I hope you see my slides.
Yes.
Okay, perfect. So then welcome to my talk. My name is Denise Karl. As said, I'm a PhD student at the German Research Center for Artificial Intelligence. And together with my co-authors Marc Roublet and Antonio Krüger, we investigated to what extent a physical object can differ in size from its virtual representation in optical see-through tangible augmented reality. And we decided to take a closer look at tangible augmented reality because studies have shown that users prefer to interact with tangible objects rather than with purely virtual ones, because this allows for more intuitive interaction. And this would mean that ideally one would need an exact matching physical prop to interact with its virtual counterpart. But this would then require the production and the storage of a very large number of physical props, which is simply not feasible. So therefore, it would make more sense to have a small number of physical props that are suitable for multiple use cases so that one physical object can represent a large number of virtual objects. However, this would result in the tangible objects being visually different from the virtual objects they represent. And therefore, it is necessary to investigate to which extent this virtual and physical objects can differ in terms of visual characteristics such as size, shape, and texture. And in both virtual reality and also video see-through augmented reality, there are already some studies that address this issue. And we now examine it for the first time in optical see-through augmented reality, which differs from VR and video see-through AR in the way that the overlays are slightly translucent and you can still perceive the physical objects behind them to a certain extent. So for us, it is important that each factor is considered individually. So before combinations of them, such as a change in size and shape, are analyzed. And therefore, in the first step, we determined whether a physical object can deviate in size from its corresponding virtual object in optical see-through augmented reality. And here we looked at the influence on usability and performance, as well as on the perception of presence. We examined both the augmented reality presence, which indicates the extent to which the displayed overlays look real, and also the tangible augmented reality presence, indicating how real the interaction with the virtual objects feels. In our study, we wanted to find out if there is a size range in which usability, presence, and performance do not differ significantly from our baseline condition in which we used an exact physical replica. So our base condition is the condition M, with an object length of 6 centimeters. And overall, we examined 7 different size conditions, ranging from -50% of the base length named condition XXS to +50% of the base length named condition XXL. And yeah, the size of the physical objects remained constant throughout the study, and we only changed the size of the virtual objects. 3 different objects were interacted with. So the shapes were chosen in such a way that there is only one way to place them on suitable target objects, and that the maximum rotation of the objects up to 180 degrees is required. Now, all objects had a length of 6 centimeters and a width and height of 4 centimeters, so that they're easy to grasp. And to enable the visualization of the AR overlays at the location of the physical props, it was necessary to track the proxy objects in space. And for this, we used an OptiTrack motion capturing system. And the physical objects we used were equipped with black marker trees for this purpose. And these were designed to be long and thin so that during the interaction with the objects, the tracking is not disturbed by the marker trees that are too close to each other. So the objects were displayed using a HoloLens 2, which also had to be tracked in space in order to be able to place the virtual camera at the correct position. So we also equipped it with 3 markers. Our study took place in a darkened room, which was only dimly lit, and we used black physical objects with white overlays and set the HoloLens brightness to 100% to achieve a maximum opacity of the overlays. The participants performed two tasks each. So the first task really served to gain a feeling for the interaction with the virtual objects without any time pressure. And here the participants had to assign each of the 3 objects to 6 virtual 3D targets, which were displayed in the air, one after the other. And both tasks were repeated for all size conditions whose order was balanced. And in the second task, the participants then had to align all 3 objects simultaneously on given 2D targets as quickly and as precisely as possible. And as soon as one of these objects matched its corresponding target, its overlay turned green, and then the task was solved when all overlays were green. In both tasks of the study, the physical objects had to be placed quite accurately for a task to be considered solved. And for this, we used thresholds we determined in pre-studies that provide the best mix of feasibility and complexity. The procedure of the study was always the same for each participant. So first, the HoloLens was calibrated to the eyes of the participant using the eye calibration application of the HoloLens. And then the application was started with fixed initial orientation of the HoloLens. And subsequently, a fine calibration of the eyes was performed, which was especially necessary when the participants wore thick lenses or had a large interpupillary distance. For fine calibration, a red cuboid was virtually displayed on a black cuboid, and if the position of this physical and the virtual cuboid did not match, the position of the virtual camera was manually adjusted until this was given. And this ensured that all overlays appeared in the correct position during the entire study. And to ensure that the objects were always in the field of view, the participants had to align their heads so that a virtually displayed border roughly matched a marked region drawn on the table. Subsequently, the physical objects were placed on a plate by the study leader and then were covered with a box and then placed in front of the participant. And as soon as this box was removed, the overlays and targets appeared and the task started. And by lifting the box, also the time measurement in task 2 started automatically. And after completion of each size conditions, 3 questionnaires were given, the AR and the tangible AR presence questionnaire and the size perception questionnaire. And this questionnaire asked to what extent the sizes of the virtual and physical object matched and how disturbing it was to grasp and interact with the objects. And after completing all the tasks, another final questionnaire had to be filled out, answering demographic questions as well as ranking the conditions. The figure you see here shows the results of our study for the individual size conditions. So on the left, you can see the measures we looked at. In the upper area, the perceived disturbance during grasping and interacting is shown. And below that, the results for the perceived AR and tangible AR presence are displayed, followed by the size estimation of the virtual object compared to the physical object and the performance measured in terms of task completion time. The bars you see indicate the range, there was no significant difference between the particular size condition and the base condition M. And the blue bars show the results for task 1 and the orange ones, those for task 2. The significant differences are marked with 1, 2, or 3 stars based on their significance level. Overall, one can see that the differences between task 1 and task 2 are very small. And the biggest difference here can be seen in the estimation of size. So in task 1, the participants were not able to distinguish condition S or condition L from the condition M. But then in the second task, a correct size estimation was made. And this is probably due to the learning effect, since task 2 was always performed after task 1, which may also then explain the slight differences in the other measures. Regarding disturbance in grasping and disturbance in interacting, it can be seen that both slightly smaller overlays, so condition S, and slightly larger overlays up to condition XL are possible without significant degradation. And then in terms of the AR and the tangible AR presence, even larger overlays are possible without significant degradation, at least until condition XXL. But with the size conditions selected in the study, it was not possible for us to identify an upper limit. So it may be also possible to use even larger overlays, here, but yeah, the values we have seen suggest that there is an upper limit here as well at some point. Regarding task completion time, we found no significant differences from baseline condition M. What we can see from the results of the study is that small size differences cannot be reliably detected if no prior knowledge about other better fitting objects exists. And it is possible to vary the size within certain ranges without significant worsening of performance, usability, and presence. And the size variation range in this case is wider for virtual objects, larger than the physical object, than for smaller virtual overlays. And overall, this shows that it is possible to use one single physical object as a tangible prop to interact with several virtual objects of different sizes. But there are also several limitations. So we determined no exact limits as how much one can increase or decrease the size. So appropriate methods, such as the up-down staircase procedure are needed in further studies to determine these limits. And we also used a fixed lighting condition chosen to make the overlays appear as opaque as possible. And therefore, we found out the results are very close to results from VR and video see-through AR. However, in reality, the lighting is not as constant as in the laboratory. So one next step here is to investigate how the lighting influences the results. And finally, we have only studied size so far, so other characteristics such as shape variations need to be examined in further studies. And for more detailed information on the study conducted and its results, please refer to the corresponding paper. Thank you.
Thank you for this very interesting talk. So let's check if we have a question. Not yet. So I'll ask. Well, in fact, I do have a lot of questions. Do you grasp any effect of the transparency during the experiment? Does maybe less or more transparency would help for the interaction? Would it be even noticeable? Or what would be the impact of this change in transparency?
Yeah, so I guess it will have an effect because when you can see through the virtual objects more, then you perceive this physical object differently. So maybe then it is really difficult to grasp one of the objects because you don't know which one to grasp, and maybe then you switch a different one. So I guess that this will make a big difference.
And during the interaction, does people try to, grab first the virtual object and then adjust to grab the physical one, or it was just a blended action on how do they react when there is a big difference between the physical and the virtual object?
Yeah, interestingly, we had two parts of people, one who liked the smaller ones best and the others who liked the bigger ones best. So that's was totally interesting. So yeah, they always try to grasp the virtual object because so especially in the when the virtual overlays were larger, because with our lighting conditions we chose, it was really so bright, the overlay, that you could not really perceive the physical object behind it. So they were trying to grasp this big one and then really went through it. And yeah, the reactions were, yeah, okay, when you first grasp the object, it's irritating, but then when you have it in your hand, then it's easy to rotate it and match it.
Okay, and did they change their interaction technique, the way they were grasping the object according to the size of the object, or it was always the same movement?
Interestingly, only one thing we recognized was that when the overlays were bigger, then most of them used 2 hands to rotate them, and when they were small, they only used 1. That was interesting, but yeah, that was the only thing we really recognized.
That's interesting. Thank you. Thank you very much for this talk. So we'll now go ahead and continue with our second speaker, who is Mohamed Ben Machoub, who is a PhD student at the Department of Radiology and Nuclear Medicine in the Biomedical Imaging Group of Rotterdam. He will be presenting his paper entitled Virtual Extensions Improve Perceived-Based Instrument Alignment Using Optical See-Through Devices. So Mohamed, you can share your slide and start your presentation.
Yeah, thanks. Right. So good morning, everyone. I'll be presenting the article Virtual Extensions Improve Perception-Based Instrument Alignment Using Optical See-Through Devices. So I am Mohamed Ben Machoub. I'm a PhD candidate in the Biomedical Imaging Group, Rotterdam, Erasmus MC, and I'm supervised by the professors Vero Nissen, Epo Wolfius, and Theo van Walsum. So in many types of surgeries, specifically cranial or orthodontic surgeries, surgeons make use of navigation systems to achieve preoperative planned outcome. And for this, they use patient-specific data such as CT or MRI, in addition to tracking systems to track the anatomy and the instrument to perform, let's say, for example, an operation such as a drilling surgical operation. Now, these conventional navigation systems come with different challenges. The first one is the hand-eye coordination. So what you can see in the picture is that the surgeon is trying to drill from top to bottom, but he's seeing his drill actually going from left to right, which is really not intuitive. The second challenge is that surgeons keep switching the focus from surgical side to screen and going back and forth, which is not convenient. And the last challenge would be that a surgeon is working on a 3D environment, but what he's getting as a feedback is 2D images. And actually, this requires the surgeon to mentally reconstruct the 3D aspect of the anatomy, which is sometimes hard to do. Now, in the literature, augmented reality has been suggested as a solution to these challenges. So it mainly could solve the hand-eye coordination and the switch of focus, because you have the anatomical the models projected on the anatomical or surgical site. But for the depth perception, it's still challenging in AR navigation, even when using optical see-through devices. So some studies in the literature pointed out that there is a depth underestimation in matching and reaching virtual objects using see-through devices. So actually, it's kind of a problem, because surgeons generally try to reach an anatomical target or follow, let's say, pre-planned trajectory, as you can see here in the picture. But because of this underestimation of depth, 2 objects may seem aligned from top view, as you can see, but if you check from a side view, you can see that they are actually misaligned. So this actually would force surgeons to look from different sides and from different point of views to notice this misalignment. So to account for this, Martin Gomez and others suggested virtual mirrors. So what you can see here are virtual mirrors, and it gives different point of views of the aligned objects, and you can spot the misalignments on the mirror, and you can account for it. Moreover, so Payar and others found that users can estimate the distances between virtual objects more accurately. However, these findings were not reflected on the augmented reality navigation systems that we found in systematic review that we performed on AR for craniomaxillofacial surgery. And so what we noticed is that 18 articles had shown augmentations of instrument, whereas 21 didn't. And so this Therefore, the goal of this study is to answer the following questions. So is instrument augmentation important? In other words, should we rely on egocentric or exocentric alignment? And also, can we improve fine motor skills for instrument alignment tasks when using optical see-through devices? So for this, we used an augmented reality system composed of Microsoft HoloLens 2, an electromagnetic tracking system, NDI Aurora, and also 6 degrees of freedom pointer. And the task was to actually align the pointer with a pre-planned trajectory. And so the variable that we wanted to check is the visual representation. So for this, to get the users familiar with this system, so we give them some tasks, and it was to actually try and reach this sphere center. So in this one, there is no representation of the instrument, and this one there is a representation following the instrument. And a third step, we gave them more, let's say, harder task where they have to align these two blue and pink, let's say, objects, and make it as accurate as possible. And for this one, so it's the system that confirms the correct position. So the constraints were 3 millimeter on these, and here we made it even harder. So 1 millimeter on the tip and 1 degree on orientation. And so after the training session, we gave them the real task, and which is to align the instrument with the pre-planned trajectory that you see here. And in this one, the difference is that the users has actually to confirm a good alignment. So we had the first condition where there is no visualization of the pointer, which is egocentric, let's say. And we had two others where we have a real representation, and the metaphor that we call virtual extension. So what it consists of is the real representation extended by virtual disks. And this was inspired from traditional surgical navigation, where you can use 2D crosshairs to align an instrument to an anatomical target. The goal of using these virtual extensions is to provide more size to an object instead of a multi-view kind of visualization. So during this experiment, we collected some data. So we collected positional orientation error, also the average pointer and head velocities. And after each condition, we passed NASA TLX and SUS forms to be filled by the participant. So the hypothesis underlying the experiment is that we are expecting that exocentric conditions perform better than egocentric conditions, and this is because we're expecting that virtual extensions, and this one gives more, let's say, reference to make it easier for the users to perform better. And however, for the subjective measurements, we are expecting that virtual extensions would perform lower, so users will be more frustrated because they have to align more objects. So in the end, so we had 18 volunteers go through the experiments, including 5 surgeons, and in total they performed 324 alignment tasks. So for the positional and rotational error, we can already notice that virtual extensions users that perform this perform better than in real representation and in normal or in a no representation. For the pointer velocity and head velocity, they were quite similar. However, for the frustration, it was not as we expected. So users reported that they felt less frustrated using virtual extensions. We also gave them a form to see how confident they are. So we tell them to rank actually the conditions based on what they think they performed better in, and we checked this on the data. So for the virtual extensions, 15 users said that they think they performed better with this, and 14 of them actually did perform better, but only 9 actually preferred to use virtual extensions. So the virtual the focus of the study, let's say about the limitations, is that the focus of the study was on the metaphor of virtual extensions. So we didn't think of the size, the color, or the shape of the virtual extensions, or the opacity also. And also we couldn't perform like big meta-analysis on a gender or scale on the overall performance. So to conclude this presentation, we can say that exocentric conditions perform better than egocentric. So instrument augmentation is preferable in in this scenario, which is aligning instruments. And we saw also that for the virtual extensions, users performed better for positional orientation error and felt actually less frustrated than the no visualization or the normal visualization techniques. So yeah, thanks for your attention, and feel free to ask any question.
So thank you for the presentation. We have time for some questions. I remind the audience that you can ask questions in the chat or in the Q&A feature of Zoom and also on Discord. So I do have a question, in fact, so thank you for this very interesting talk. I was wondering, you said that only 9 participants prefer the virtual extensions. Why only 9? Did some participants notice some disadvantages or things they don't like on this virtual extension?
I can think of various reasons, but I would say that, for example, if you have those who preferred no visualization at all, the thing is that they felt easier to do it because they don't have a lot of references to check. For virtual extensions, I think maybe like the virtual extensions that we provided are an overkill. So we had like 3 disks, and it might kind of occlude the view of the users, and they feel like some of them felt really frustrated because they can see the misalignment so fast that they keep always trying to perform the best, and that I guess this is one of the main reasons that they prefer the other ones.
And the task was only an alignment task, so there is no other augmentation, because I was wondering if there is some overlapping issues or occlusion issues because of the size of the virtual extension.
Yeah, so the task was only on, so say it was only an alignment task. And yeah, I think if there is like, I think where they performed better, let's say, because if you have like a depth estimation of 1 to 2 millimeters that you can see on this axis, like those references would help you actually account for your misinterpretation of that depth. Yeah, so that's I guess that's what I want to say.
Okay, and do you think that how important is the shape of the virtual extension? Can we think about some specific virtual extension for some specific task, or other generic? Is the one you used seems very generic, but if you want to have something like orientation calibration, it won't be very useful because of the symmetrical form. So can we think about some, I mean, more generic virtual augmentation?
Yeah, I can think of some. So for example, for this one, why we did this kind of disc shaped is because this orientation didn't matter, so the roll didn't matter. But yeah, I can think of, for example, cubes, because cubes can give you like, if you know that they are cubes, you can see the 90 degrees from all sides, and actually this would, I would think that it would help in performing better alignment also.
Okay, thank you for this very interesting presentation. We'll now switch to our next speaker, who is Shoma Yamaguchi, who is master student at the Graduate School of Information Science and Technology at the University of Tokyo. And he will be presenting his paper entitled "No, I'm Not Afraid: reducing fear of missing out in 360 degrees videos on a head-mounted displays using a panoramic thumbnail.
Okay, can you see my screen?
Yes, perfect.
Okay, thank you. Let me start. Hello, everyone. This is Shoma Yamaguchi, a student from the University of Tokyo. Today, I'm going to talk about a paper, Now I'm Not Afraid, Reducing Fear of Missing Out in 360-degree videos on a head-mounted display using a panoramic thumbnail. 360-degree video or cinematic virtual reality provides viewers with an immersive experience. They can enjoy it moving their head freely. However, there is an inevitable problem of feeling fear of missing out, FOMO, when viewing a 360-degree video. FOMO has been identified as a negative factor that distracts viewers during 360-degree video viewing and reduces their enjoyment of the video. To solve the problem of FOMO, there have been many studies on guiding the user's gaze to the region of interest, ROI. However, there are parts of the video that are not in their field of view, FOV. Therefore, guiding the gaze to the ROI cannot necessarily solve FOMO. In addition to gaze guidance, researchers have been studying a method to reduce the region of the video that the user cannot see. For example, Lin proposed a technique in which ROIs outside the FOV are displayed within the FOV as picture-in-picture previews. However, there are also parts that user cannot see. Another study showed decreasing the display area of the video from 360 degrees to 225 degrees can reduce FOMO, but it also showed the sense of actually being there, in other words, presence, was reduced. In this study, we propose a panoramic thumbnail technique. In this technique, a panoramic thumbnail of the full 360-degree video is located at the tip of a VR controller, like this video. That allows users to refer to this thumbnail and grasp the overall view of the video whenever necessary. A gray rectangular frame indicates the user's current FOV, which makes users know where they are looking at in the video. This is expected to reduce FOMO because the users can grasp the entire video. And moreover, because the display area of the video is not reduced, the feeling of presence could be maintained. Here's our research question. RQ1 is that, can the proposed technique reduce FOMO without a negative impact on the viewing experience? And RQ2 is that, how do users interact with the proposed technique? To investigate our research question, we conducted an experiment to compare viewing with the proposed technique with normal viewing without it. In this experiment, the participants viewed 360-degree videos in two different ways: normal view, NV, and panoramic thumbnail technique, PTT. And then they answered a questionnaire, which evaluates FOMO, presence, and quality of viewing experience. In addition to subjective evaluation, we also analyzed eye tracking data and head tracking data during viewing to investigate how they interacted with the proposed interface. To investigate the role of the proposed technique in videos with different ROI types, we used 3 types of 360-degree videos with different ROI types, type A, B, and E, according to the classification of Lin's study. Type A videos have a single static ROI at any given time. In this experiment, we used a video of a local sightseeing spot, which has screen switching. Type B videos have one moving ROI at any given time. We use a narrative animation video. In this video, viewers can easily follow the ROI. Type E videos have multiple ROIs present simultaneously. We used a Pokemon video. In this video, once the viewers see some ROIs, they cannot see the others. Next, I'll explain about procedure. After explanation about the experiment, we had a practice session to illustrate how our technique works. In the former experiment, the participants viewed the first half of the video under either the NV or PTT condition and answered the questionnaire. And then they viewed the second half of the video under the other condition and answered the questionnaire. This process was repeated with 3 videos. After a total of 6 viewings, they answered a free text questionnaire about their impressions of the different viewing conditions and videos. This is result of subjective data. We evaluated 3 scales: FOMO, presence, and quality of viewing experience. The participants answered each question on a 7-point Likert scale. The answers for each item were averaged to calculate the score for each scale. An alignment rank transform was first applied, and then a 2-way repeated ANOVA was conducted. It showed no interaction between viewing condition and video type for any of the scales. For FOMO, a significant main effect of the viewing condition was found. The score of NV was significantly higher. That shows the proposed technique could reduce FOMO. Here is a result of quality of viewing experience. A significant main effect of the viewing condition was found. The score of PTT was significantly higher. That shows the proposed technique could improve the quality of the viewing experience. Finally, for presence, no significant main effect of the viewing condition was found. The presence score were greater than 4 on the 7-point scale for both NV and PTT for all videos, which suggests that proposed technique can ensure a certain level of presence. The result of the questionnaire showed the proposed technique could reduce FOMO without negative impact on viewing experience. However, in the free text responses, 3 participants mentioned that the fun of finding Pokemon by themselves was reduced. Therefore, it is necessary to explore the use of the panoramic thumbnail according to the type of video and the purpose for which the viewer is viewing the video. Some participants mentioned that the panoramic thumbnail distracted them and it decreased presence. So further studies to investigate exact effect of the panoramic thumbnail are necessary. I'll explain about result of eye tracking data and head tracking data. From the head tracking data, we calculated the angle at which the head moved per second. The results of ANOVA showed a significant interaction effect. Wilcoxon's signed rank sum test for each video type showed that the amount of looking around was significantly larger for NB than for PTT for the type A video and the type E video. Because the type B video is a narrative video, the ROI was not lost, whereas the type A and the type E videos required significant looking around because the participants missed ROIs. This indicates the panoramic thumbnail reduced the amount of looking around in the videos requiring significant looking around. In other words, the participants used the panoramic thumbnail as a substitute for looking around. We also examined the correlation between the amount of looking around for NB and the percentage of time spent looking at the panoramic thumbnail for PTT. This indicates whether the more participants look around, the longer they will look at the panoramic thumbnail. The results of the test of no correlation showed positive correlations for the type B video and type E video. According to free text responses, it is possible that some participants perceived the type A video as a mere landscape video, and the ROI did not draw their attention. This suggests that some participants looked around a lot to enjoy the landscape video, but did not use the panoramic thumbnail to search for ROIs. On the other hand, type B and type E videos have clear ROIs for the participants, and comments suggest that they use the panoramic thumbnail to see ROIs and background of ROI. These results suggest that the panoramic thumbnail was used to actively search for content outside of their FOV. We investigated when the participants looked at the panoramic thumbnail. This figure shows proportion of participants who are looking at the panoramic thumbnail according to time after the start of the video. The red dashed line indicates scene changes. That shows most of the participants watched the panoramic thumbnail at the beginning of the video. And that also shows participants did not always view the panoramic thumbnail immediately after scene changes. Accordingly, we checked the scene in which the number of participants viewing the panoramic thumbnail increased notably. As a result, we found 4 scenes that participants were most likely to see the panoramic thumbnail. Because all the participants looked at the panoramic thumbnail at their own timing, it was difficult to fully grasp the moments when the timing of looking at the panoramic thumbnail was significantly aligned. Lastly, I will talk about future works of our research. In this study, we compared the proposed method with normal viewing, but did not compare it with other viewing methods. It will be necessary to compare several methods to find the optimal method for reducing FOMO, depending on the type of video and viewing purpose of the user. And we received meaningful comments from the participants through this experiment. Using this information, we will be able to make a more user-friendly and effective panoramic thumbnail. This slide summarizes the point of my speaking today. That is all for my presentation. Thank you so much for listening.
So thank you for this very interesting talk. Do we have question? Yeah, we have question. A question from Edgar. My question is, did people complain about distortion because of the way the ROI in the thumbnail was shown? Any distortion?
Sorry, what is distortion?
I'm not sure I'm catching the question right. People complain about the distortion because of the way the ROI in the thumbnail was shown. Oh, maybe I added some question. Maybe I can reformulate because here we can see in the video, the ROI is representing moving in the thumbnail. And since the video is 360 degrees, maybe you envision some other representation. For example, the ROI being fixed in the thumbnail and the background of the thumbnail moving. Here in your experiments, the background of the thumbnail is fixed, and the rectangle is moving. Did you try the opposite?
I thought that is visible for users to they can find what they want to see very easily with this in this method, I think. But in free text questionnaire, a participant answered that the gray frame is fixed is better. So yeah, we must consider that.
And also, since the video is 360 and the thumbnail is flat, there is a deformation between the video and the thumbnail. And did you experiment issues, for example, objects who are on the floor or on the ceiling? Because they are deformed a lot in this area.
But you mean why I displayed the rectangle? Yeah.
Why if you have an object in the sky in the video, when you look in the thumbnail, it will be cropped on the top because of the deformation, right?
Maybe this is very common way to display the 360-degree video in flat screen. So I choose this method.
Okay, thank you very much for your answer. We'll now switch to our next speaker. Our next speaker is Sung Sheng, who is a master's student at the Department of Computer Science and Engineering at Iowa Women's University. And she will be presenting her paper, entitled Understanding the Two Steps Non-Visual Omnidirectional Guidance for Target Acquisition in 3D Spaces.
Okay, thank you. Can you see my screen?
Yes, perfect.
Okay. Hello, I'm Seung-Ah Chung from Women's University. I am going to present our two-step non-visual omnidirectional guidance design for target acquisition in 3D space. This work has been done with Kyung-Eun Lee and Yurano. Understanding 3D position of surrounding objects is important for users to decide whether to interact with or to avoid those objects. However, locating objects visually can be inefficient and frustrating in 3D space. Moreover, this approach may not be feasible in some situations where the visual information is difficult to deliver. For these reasons, many researchers investigated the design implication of directional guidance with non-visual feedback. However, most of the studies were limited to two-dimensional space, so we conducted a prior study focused on how to convey omnidirectional information in 3D space. In the prior study, we found that users have a tendency of scanning the 3D environment in a horizontal direction first, and then in a vertical direction for finding a target, regardless of non-visual feedback conditions such as audio or haptic. Inspired by this finding, we proposed a two-step omnidirectional guidance so that horizontal or vertical direction is provided one at a time based on the shortest Cartesian distance instead of guiding users based on the Euclidean distance, which is shorter. We conducted a user study with a target finding task to investigate 3 different feedback conditions for conveying omnidirectional guidance to users. We designed 3 different feedback conditions for the user study. First one is a vertical first condition, and we will call this VF condition from now on. It provides directional guidance to users in 2 steps. First, vertical direction with audio feedback, and then horizontal direction adding the haptic feedback. It plays a beeping sound repeatedly to guide users towards the target height. So the final movement looks like this. We set the blue region, which looks like a disk, to indicate the vertical position of the target. When the region is reached, continuous vibration is provided to inform the users to stay the height of their arm. Also, same beeping sound is played again to guide the user to the exact 3D position of the target. Second one is the horizontal first condition, and we will call this HF condition from now on. It provides the guidance similar to the VF condition, but in the reversed order. A horizontal direction is provided first with audio feedback, and the vertical direction is followed with haptic feedback. So the final movements looks like this. In the HF condition, the blue region, which looks like a piece of pie, indicates the horizontal position of the target. When the laser is in the region, vibration is provided continuously to inform the users to keep the direction of their arm. The beeping sound is played repeatedly to guide the users to the blue region, in this case, the target direction, or the exact 3D position of the target. We also designed a one-step guidance called NO condition to compare with the first 2 conditions. In this condition, there is no certain order when finding the target objects. So the final movements looks like this. We set the blue region to inform users that the laser baitcast is near the target. The beeping interval decreases as the laser gets closer to the exact 3D position of the target object. For the experiments, we built a virtual reality environment using Unity running on the desktop computer. A handheld controller of HTC Vive Pro I and external speaker were used to convey the output feedback. As for the target finding task, 10 sphere targets were used. All of them had the same distance between the position of the participants and itself. We played a beeping sound for audio feedback. Its interval decreased as the pointer got closer to the target region or the exact target position. Also, when the pointer was in the blue region, we turned on the vibration motor for haptic feedback. It informed users that they found the target's vertical or horizontal position, or the target was nearby. When the users pointed at the target, they received short and strong vibration feedback along with a chime sound for confirmation. We conducted a user study with 12 blindfolded participants. They were asked to point 10 virtual targets using a handheld controller under the 3 conditions. After that, we asked them the subjective feedback of the conditions, including preference and ratings. As a result, the average time was shortest in HF condition, followed by VF, then NO condition. The time difference between VF and HF is not found to be statistically significant. However, two-step guidance conditions were more efficient than a one-step guidance condition. Similar to this, the average distance was shortest in HF condition, followed by VF, then NO condition. To be more specific, it is found that the travel distance under HF condition was significantly shorter than other 2 conditions. We also analyzed the duration of each step of two-step guidance to find the effect of searching direction. We found that participants were faster under HF condition than VF condition in horizontal search. On the other hand, they were faster under VF condition than HF condition in vertical search. These results were also shown on the travel distance. When we analyzed the participants' traces, we found some interesting results. Participants tend to make less sudden changes in directions in the two-step conditions than one-step condition. They felt some confusion about which direction to move once they received guidance for vertical or horizontal direction. However, the number of sudden directional changes was more prevalent when finding the exact target location in NO condition. In addition, the tendency of finding the target direction first before finding the exact position in 3D was confirmed under NO condition. Finally, we analyzed ratings of each condition evaluated in a 5-point Likert scale. Most participants perceived that all 3 feedback conditions are easy to understand, particularly for the HF condition. Similarly, HF condition received the best ratings in terms of fatigue and satisfaction. Reflecting the results of subjective evaluation, HF conditions received the highest number of votes when asked the preference. The main reason was that finding horizontal direction first is less exhausting since they do not have to stay their arm in specific heights. On the other hand, 5 participants preferred the VF condition more. It was because they felt they moved their arm less so that the condition was comfortable. Our two-step guidance was designed based on the shortest Cartesian distance. It is longer than the Euclidean distance, which is the basis of one-step guidance. However, the findings show that our two-step guidance is faster with shorter travel distance than one-step guidance. Also, we observed the tendency of dividing the task into 2 steps even under the one-step guidance. This could be due to the low cognitive load since the participants could focus on one direction at a time with two-step guidance. Also, we found that HF condition showed better performance than VF condition in terms of travel distance and subjective evaluation, especially on fatigue and satisfaction. This could be due to the gorilla arm problem, as finding the horizontal direction of the target while lifting one's arm at the target height is physically more difficult. Thus, we recommend giving two-step guidance in horizontal direction first for informing the target's 3D position. Our findings show that the participants were faster in the first step than the second step in two-step conditions. Extra cognitive load during the second step can occur as participants had to focus on performing 2 subtasks with multiple output modalities. It can be also explained by ballistic and correction phases of goal-directed 3D movements, where rough movements were made in the first step and fine adjustments were made in the last step. Although we confirmed the effect of non-visual guidance, we observed the sudden changes in direction occurred by the confusion of deciding direction in the first move. We used proximity-based feedback through different modalities to reduce the distraction from conveying different types of information through the same channel. However, further investigation about the effect of specialized sounds on the performance of two-step guidance is needed. Although we try to map the vibrating region based on the size and the distance of the target, we believe that region can be optimized. If the region is set too big, the region itself can be found easily, but the search space within the region is still too wide to find the accurate target position. For example, we noticed that our blue region of any condition was set to white, that the traces for any condition have zigzag motion near the target. On the other hand, if the range of the region is too small, users would not benefit from the additional cue since finding the region can be difficult as much as finding the target. We used audio feedback mainly to convey the information. However, there are some difficulties to rely on audio feedback in a noisy environment. Also, listening to the surrounding environment sound is important for safety. Thus, bone conductive headset or another modality feedback such as haptics should be reconsidered. Also, there are some limitations to apply the system in the real world, as we assume that the target position is known and that users' pointing direction is detected. Thus, technologies should be improved for tracking one's pointing finger or recognizing a target's 3D position, including depth in a real environment. As for the implementation of such a system, a wearable camera that can generate 360-degree panoramic images should be considered to detect surrounding objects. For the summary, we proposed two-step omnidirectional non-visual guidance for finding a target in 3D space. We found its effectiveness compared to one-step guidance by conducting a user study. The findings show that our two-step guidance outperforms the default condition, especially when the horizontal direction guidance is provided first. Based on the findings, we plan to extend our work by applying and evaluating the design, focusing on conveying the frequent changes in object's direction with respect to users' location in both virtual and real-world environments. This is the end of my presentation. Thank you.
Thank you very much for this great presentation. I'm checking if we have question. Not yet. I will ask a question. So, did participants have a way to stay at the previously proper position? I mean, for example, when they're moving in the first vertical position, they find the proper vertical position and then they have to adjust the horizontal position. And if during this adjustment, they are moving in the vertical axis, do you have a way to prevent that, or people do not feel this problem?
Oh, we set the blue regions that gives the vibration. So if in VF condition, for example, participants found the blue region and then they turn around in the horizontal direction and they flip for the region, and then they do not have the vibration feedback. So they thought, oh, I missed the region. So they, correct the direction.
Okay, and so the blue region was big enough to be sure that they come back to the proper position, right?
Yes, we set it for the big regions for the VF and HF conditions.
I see. Another question, you mentioned that you were thinking about using other modality like haptics or vibration to guide the gesture. Did you think about using different modality for different axes? For example, the sound for the vertical axis and the vibration for the horizontal axis. Is it something that will be used in real interaction?
Oh, yes, we considered about that, but we thought that when we give the different information for same information through different modalities, it could be confused it could give the confusion of the participants. So we set the information in same channels and gives another information to stay your direction or stay your heights of the arm. So in different haptic feedback.
Okay, and also we also have a question from Bruce Thomas, who is wondering, you used 2 degrees of freedom for the rotation. Do you thought about 3 degrees of freedom rotation for the handheld device?
I didn't catch that. So is the question meanings of the controller's rotation?
I think the question is, did you consider the rotation alignment, I guess? Bruce?
I don't know, is it right answer for that?
Yeah, because here you were only considering the position of the handheld device. Did you consider twisting the handheld device and asking people also to align the rotation of the device?
Oh, that's one of the limitations, that we did not control of their arm in a specific position, but we used the controller which provides the laser raycast. So just twisting is not considered for that, just laser raycast.
Okay, thank you very much for your presentation and your answers. If you want to continue this discussion, we can also meet after in Gathertown. But now we'll switch to our next speaker, who is Thibaut Fabre. He's PhD student at the University of Tokyo, and he will be presenting his paper entitled Investigating Textual Sound Effects in a Virtual Environment and Their Impacts on Object Perception and Sound Perception.
Sorry, my Zoom crashed. Thank you for the introduction. So I will start the slide shortly. Sorry again for the small delay. Okay, so thank you everyone for being here. Today I will present you my paper, our paper, titled Investigating Textual Sound Effects in a Virtual Environment and Their Impacts on Object Perception and Sound Perception. This project was made thanks to the funding of the Erato Jizai Body Project. So the title may be a little hard to understand at first, but it's rather simple actually. We want to bring the concept and qualities of comic book onomatopoeias to virtual realities. So for this purpose, we choose another name to better distinguish onomatopoeia as a linguistic term and onomatopoeia as a style effect. So we chose to use the word textual sound effect, text effect, or TE for short. So TE make use of audiovisual cross-modality concepts, meaning that they can both affect auditory and visual perception. And thanks to the linguistic nature of onomatopoeia, the word, the text we display carry meaning by itself. So when you see honk, you just think about the honking sound it describes. And this aspect is present in onomatopoeia in a lot of language around the world. So there's no shortage of related works on presenting text in VR or in audiovisual cross-modality, but we only found a few papers that bring the two together and make use of onomatopoeia. So here, this is 2 papers from a Korean laboratory where they did something that is pretty close to our research. But they highlight the potential of textual sound effect by showing their impact on presence and immersion with no significant difference in realism. So these papers are still very much on the surface and what we can do with textual sound effects. So from our study of audiovisual cross-modality, we devised 5 hypotheses. The first 3 are about visual perception. So H1 and H2 refer to an object material classification. H1 is about a congruent text effect. So a text, for example, for a wooden sphere, if you see a wooden knock on top of it, you will categorize it as wood faster than if, for example, you see a metallic knock on top of it. And H2 is not about the speed, but about the actual categorization. Then we have H3, which is about the material properties. So it's about the material adjective, if you will. For example, the sphere wetness or temperature. Then we have the last 2 hypotheses which refer to sound perception and are more straightforward. For example, a TE has an impact on the perception of the sound volume, and a TE has an impact on the perception of the sound location. So to check our hypotheses, we made a 4-step experiment. The first part of this experiment is focused on visual perception. Step A1, the user is seeing a sphere falling periodically on the platform. And upon hitting the platform, there's a TE appears and the visual and sound effect of the material is revealed. Then the user has to classify the sphere as wood or metal as fast as possible. So there is only a wood or metallic visual, sound, or text effects. We measure the reaction time, which is their time to answer, and the actual answer of the participants. Then we have step A2, which is where the user will interact with the sphere by hitting it, and a knock onomatopoeia will appear. However, so in this step, the onomatopoeia is always congruent. It's always a wooden sphere. However, sometimes there will be a water effect on the text. So either the text will be changed to splosh or have water particles around it, like on the video here. And then we ask a Likert scale. On the Likert scale, we ask them some questions about the wetness or the temperature of the material. So for the result of step A1, which was about the categorization, we see here that on the reaction time graph that there is a significant increase in reaction time for a non-congruent text effect when compared to a congruent text effect. So this is seen on the graph and is actually statistically significant. More interestingly, when we compare the control condition of no text effect with congruent text effects, the brown and the green bar here, the decrease in reaction time is also significant. So this means that TEs are processed by people, so this is encouraging for us. And also one last thing to note is that the difference in reaction time with a non-congruent TE, so here when compared to a non-congruent sound or visual, is not significant. So these three bars, the difference are not significant. Then we have the results on the categorization itself. I will be a bit faster here because there is absolutely no significant changes on the material classification. So this graph shows the number of time users answered. For example, if the sphere was visually wooden, well, they would answer wood, or visual metallic, they would answer metal. And obviously, when metal or when visual or sound are congruent, well, it's really high. But interestingly, when the text effect is on view or is incongruent, well, there is basically no effect of the text effect, and this can also be seen where if with an incongruent sound we have no bias toward the visual, and it's still 50-50 basically between sound and material. So now we move on to step A2, which was about the interaction and the wetness and the material properties. So on this interaction plot, we can see the most interesting one is here, the wet or dry question. We can see on the x-axis that the presence of water droplet do increase the number of users who evaluated the sphere as wet, but not only the water effect, but also the text use. If we only change the text and not add any water droplets, users still tend to rate the sphere as wetter. Other interesting result is that users rated the sphere as colder with the presence of water droplets, and this result was significant, although it's a bit less skewed toward cold. So now we move on to part B of the experiment, which was focused on auditory perception. So the first step was step B3. The user is facing a speaker, and the speaker replayed two sounds in succession. These sounds are accompanied by a text effect, which will be of different size. So the text size will be different. And we then ask the user to rate the second sound when compared to the first sound as quieter, the same, or louder. Then we have step B4, which is basically a reproduction of the ventriloquism effect. The user starts with their back facing an area of speaker, and they will have to locate the sound source. However, another speaker different from the sound source speaker will have either a text effect or a text effect that is only made of symbols on top of it. And here we try to see if users will rate the sound source as closer to the text speaker or as closer to the actual sound source. So does just indicating the sound source with a text or with a more standard like wave effect of sound can bias users toward answering toward the wrong speaker, basically. So for the result of the volume, so on B3, we can see that on the y-axis, if the values are positive, you mean the sound was rated as louder, and negative means it was rated as quieter. So this graph is pretty much what we expected. We see a difference in pretty much all categories when the second text is smaller, it is rated as quieter, and if it is second text is bigger is rated as louder. However, the only significant difference is when we compared the growing text versus the shrinking text. So this means that users are biased by the text effect, but only when the difference is significant. So this means that users tend to rate louder sound associated with bigger text as louder than those exact same louder sound associated with a smaller text. And about step before, I'm going to go a bit fast here, but basically we find here on this graph also that so when on the y-axis, value closer to 0 mean that the user answered more toward the text speaker than toward the sound speaker. And basically the correct answer, if you will, is the diagonal. So for example, here, if the speaker offset on absolute value is 0, it means that the correct answer was 0. And if it's 4, it means that the correct answer was 4. But we do see here, however, that when there was no text effect, the users did rate very much close to the correct answer. However, the text effect did bias significantly users toward answering where the text is and not the sound. But it's not exactly where the sound is. They still saw that the sound weren't coming from the text, but they were still biased by it. And also, interestingly, the text part of the textual sound effect did not play any significant role in this result, because both the symbol-only TE and the text TE had no significant difference. So now we'll discuss a little bit our hypotheses and see if we validate them. So for H1 and H2, we can validate H1 because we saw a significant change in reaction time, but we have to reject H2. So from these results, we can get that TEs are processed and considered by users as additional information when classifying objects. However, the information that is brought by these TEs are weaker than those of the sound or the material itself. Then we have H3, which we can also validate thanks to the wet or cold, wet or dry answers. And H3 not only means that we can affect a material property perception, but that TEs can also have some symbols on top of it. So we can stack text and symbols, and the two will make a whole. However, the TE needs to be somewhat related to the effect you want to achieve, obviously. For example, the sharpness of the sound or the roughness of the material were not affected at all by the water effect we had. This can also mean that TE can be considered as an extension of an object evolving in the same perceptual space. Then we have H4, which you can also validate. However, like I said, the change of size between the two text effects needs to be significant enough. And here we only checked this when comparing two sounds, because it doesn't really make sense with a single sound because there is no thing to compare it to. Then we have H5, we can also validate. However, this was expected from the ventriloquism effect. But the interesting result of this is that there is no difference between symbolic or textual characters for localization, at least in our setup. So from all of this study, we want to showcase the use of textual sound effects. They provide new way to interact or describe the environment. More research needs to be done about the actual potential of TEs, how to get the most out of them, and if they can affect things other than perception. And also, textual sound effect will not only be useful for entertainment purposes, but also to help the hearing impaired part of the population. But here, more work needs to be done still. So thank you for your attention, and if you have any questions.
So thank you very much for this great presentation. Do we have question? Not yet here. Okay, so I do have some of these because I'm really interested by the first experiment you described. Do you think that, did you try to use not textures objects to be sure that your virtual augmentation was, representing what you wanted to represent it?
So I'm not sure I understood the question correctly, but for example, when the sphere was falling, it wasn't textured, so there wasn't any visual impact for the users. And it's only upon hitting the platform that every single stimuli appeared at the same time. But you still have some texture on the, sphere, right? Yeah. Yes. So did you try to use no texture at all? I mean, just white or whatever color to be sure that your sound and sound representation are accurate? Yes, we did actually. We had a condition where, so the sphere wasn't pure white as it is when it's falling. We hid it behind a curtain in the virtual space. But however, the results were not really significant or interesting because we couldn't really compare them to everything else. I mean, the number of parameters were way too high to reach any significant conclusion if we added everything.
Okay, and also, do you think that we can enhance the effect of this textual sound representation? For example, if the environment is more cartoonish, for example, do you think that this representation will have a stronger effect?
So yes, this is a very interesting question. I do think that the realism of the scene plays a small impact. I base this from the two papers I cited in the related works. However, I think that we also tried a setup in AR, and the results were also pretty conclusive. Users did like it, although we don't mention this in the paper. So I think there is potential for using it in real life. But yes, I do think that if you want to evaluate realism or immersion, a more comic style environment is necessary.
Thank you very much for this talk and this presentation. We'll now switch to our final speaker, who is Alejandro Martin Gomez, who is a PhD candidate at the Technical University of Munich and research assistant at Johns Hopkins University. He will be presenting his paper entitled The Impact of Focus on Context Visualization Techniques on Depth Perception in Optical See-Through Head-Mounted Displays.
All right. Just give me a second to share my screen. Okay, thank you very much for the introduction. And on behalf of my co-authors, I'm happy to present our paper entitled The Impact of Focus and Context Visualization Techniques on Depth Perception in Optical See-Through Head-Mounted Displays. So for centuries, philosophers and physicians have tried and dreamed of visualizing anatomical structures located inside the human body. A clear example of this is the drawings from Andreas Vesalius from the 16th century. And by then, creating these drawings required dissecting cadaveric bodies. And nowadays, augmented reality has shown the potential to make this happen. For example, early work from Bahur and collaborators in 1992 showed that it was possible to consistently visualize ultrasound imagery within the patient body using what they call synthetic holes. This technique showed the potential to assist the physician during the insertion of biopsy needles using ultrasound. And it was later extended for the visualization of anatomical content in laparoscopic procedures. More recent work, such as the one presented by Bichelmeier and collaborators, implemented focus and context visualization techniques. These techniques enable in situ visualization of hidden objects of interest, while simultaneously provide contextual information of the superficial layers. Although these techniques enable the adequate visualization of virtual content in situ, they have something in common. And this is that they were implemented using video see-through head-mounted displays. Using this technology allows for realistically occluding the real world using the virtual content. And this is particularly important as occlusion is the strongest depth cue and allows creating an idea of the relative depth of the objects observed in our environment. The observation of misleading visual cues can easily trick our visual system and lead to optical illusions. This problem frequently contributes to perceiving the virtual content floating on top of the real objects, even if the virtual content is allocated accurately. So this raises the question of what happens when it's not possible to provide consistent occlusion, and how would this influence the observer's perception and the estimation of the virtual object's depth? This is particularly relevant when we want to implement focus and context visualization techniques using optical see-through head-mounted displays.
In this case, the additive nature of the display impedes the generation of black, which is a color that is frequently used to generate virtual content that occludes the real one. This problem reduces the overall effectiveness of these visualization techniques. So therefore, in this work, we investigated how the depth perception of virtual content in situ is affected by the additive displays commonly used in OST HMDs. In addition, we propose a composing existing focus and context visualization into different visual properties to provide a useful framework for further exploring the design of such techniques. Furthermore, we introduced non-traditional techniques such as chromatic shadows and hatching techniques to provide additional visual cues and overcome the limitation of the commercially available OST HMDs. To evaluate the effect of these techniques for depth estimation in situ, we compare the accuracy when utilizing VST and OST HMDs first. Our experimental setup consider a tutorial and an evaluation scenario. 32 paid volunteers gave their consent to participate in the study, and none of them had previous experience with the system. A total number of 96 different estimation trials were performed for each participant, and objective data regarding accuracy in position and time to completion were collected. In addition, participants were asked to answer the NASA TLX and the single DC question to collect subjective data. Then we used 3 traditional focus and context techniques and a baseline visualization during our first study. We later implemented them using a VST HMDs as well as with OST HMDs. The study included a tutorial stage that helped participants familiarize themselves with the task and the input device. And after the tutorial, participants were randomly assigned with one of the 2 headsets and asked to complete the estimation trials. Once completed all the tasks with that specific device, participants completed the remaining alignment trials using the other headset. Although our statistical analysis investigated the results for multiple objective and subjective measures, due to the time restrictions during the presentation of this work, only the most relevant results are discussed here. In this regard, we found that all visualizations perform worse on OST than on VST regarding the alignment error. On average, participants perceive the virtual content further away than the real when using the OST display. And conversely, participants slightly position the virtual object farther than the real in the VST condition. In terms of object position, the largest error was observed for the mid position, being significantly different from the near and far conditions. Interestingly, significant interaction between display type and target position was observed. Our study showed that participants aligned the virtual content more accurately when using the VST at the mid position. And in addition, our statistical analysis shows significant difference between the display type for all visualizations, while the comparisons for visualizations when using the same display type were non-significant. Lastly, regarding the subjective measures, virtual window consistently scored best, while virtual mask scored worst. These results, in combination with feedback from the participants, help us to identify 2 important features that reduce the effectiveness of existing techniques in OST. First, the inability to render opaque black affects the visual outcome compared to VST, particularly for the contextual anatomic mimesis and the virtual mask. And second, the display contrast reduces the visibility of shading details, for example, within the interior surface of the virtual window. These results made evident that there is a need for more specialized visualizations that adapt specifically to OST HMDs. To evaluate how these focus and context visualization techniques could be improved using OST HMDs, we performed a second study using the Microsoft HoloLens 2. The experimental followed the same design of study 1, with the difference that 27 volunteers performed 162 estimation trials. And in addition, we did not assess the NASA TLX or the single easy question this time, but introduced a rating for visual attractiveness using a 7-point Likert scale. For more details, we invite the audience to please refer to the paper. To perform a systematic evaluation of the characteristics of the existing methods, we decompose the techniques into 3 orthogonal properties. First, based on the exterior visualization as presented by the virtual window, the contextual anatomic mimesis, and the virtual mask. Second property, consider the interior rendering. In this regard, to investigate how the display's contrast affects the visibility of shading details, we propose the use of constant and shaded features. In addition, we propose the use of hatching techniques that it's commonly used in illustrative rendering as a means to provide bright overlays, regions that would appear solid and occlude the real content, while at the same time, we'll add texture to an otherwise featureless surface, and we'll support the acquisition of additional depth information by recurring to motion perspective. Lastly, the third property involves the shadow representation. In this regard, we observe that the disappearing dark regions could be mitigated by compressing the intensity range, basically mapping black to gray. And then these gray areas will provide a better border or understanding between non-augmented regions and areas that are augmented but black. In addition, we propose using chromatic shadows to introduce additional contrast through chrominance differences. Therefore, for every visualization, we would have 9 possible combinations considering the other 2 characteristics. This figure, for example, depicts the 9 possible combinations using the hole inspired by the virtual window. The ghosted, inspired by the contextual anatomic mimesis. And the mask that it's inspired by the virtual mask. Similar to study 1, this slide only presents some of the most relevant results from the study. Again, I invite the audience to refer to the paper to find out more about our results. But in terms of exterior visualization, we found out that the mask performs poorly in terms of alignment accuracy and subjective metrics. Even the combinations that add a brighter background cannot improve on the error metrics. And the hole and the ghosted perform similar for error metrics. However, it seems that participants prefer whole visualizations over the ghosted techniques. And this is quite interesting, given that the whole is one of the earliest works for in situ visualization in AR. In addition, the analysis of the interior rendering revealed that participants prefer the addition of interior geometry, either a shader or hatch. And hatch modifications outperform constant shading in terms of error. Moreover, shadow representation interacts with the exterior method, showing that bright shadows work better with whole and ghosted exteriors. Interestingly, although the chromatic shadows help improve the alignment only in some cases, they showed a positive effect on subjective metrics. Therefore, they could be beneficial in circumstances where usability is of substantial importance. Furthermore, our statistical analysis showed that participants perform better with ghosted than mask at near and mid positions, and better with whole than mask at the mid position. In conclusion, developing techniques for in situ visualization is often guided by a specific application case with unique constraints. The conceptual decomposition presented in this work can be used to explore the design space of such visualizations for both OST and VST technologies, potentially adding new variants or novel dimensions to the proposed scheme. We believe that users benefit from the adaptation of visualization techniques designed to provide optimal visual cues for specific tasks, especially in the context of medical applications, as well as for several near-field augmented reality approaches that require this type of visualization. In addition, we hope that making explicit the visual dimensions involved in the design of the visualization techniques will assist researchers in developing novel techniques suited to specific needs. And lastly, we hope that the structure analysis presented in this work can serve as a model for future extensions and contribute to forming the basis for future investigations of in situ visualization. This is pretty much all from my side, and now I'm open to any questions.
So thank you very much for this great presentation, very interesting. We have time for very quick questions. In fact, we have some of these in the Q&A. So first question, do you imagine there will be a perfect OST and a perfect VST HMD? Will it be still important differences in your kind of medical application?
Well, I think it's hard to say if they will be a perfect OST and VST, right? It will pretty much depend on the application, right? There can be some specific HMDs designed for specific applications. We can even see that on the design of the visualization technique. So I wouldn't dare to say there will be a perfect OST or VST that will work for everything. However, they can be HMDs designed to specific tasks that I would agree on that. And for the second part of the question, I think there's definitely some importance, right? Like differences. Like, for example, a very common or a well-known problem on a VST device is that if the system fails, then on a medical application, that can be a bit dangerous, right? Because then the surgeon will be basically blind, or they will need to remove the headset. However, for some other applications, using VST devices will be suitable for the task.
Thank you. And the other question is about the positioning error of your calibration. Did you evaluate the positioning error between the displayed image and the ground truth location to compensate or to evaluate for the user and eye coordination?
All right, I'm not sure if I grasped the whole question. I don't know if you can repeat it.
Did you evaluate the positioning error between the displayed image and the ground truth location? Because your current validation included the error of the user and eye coordination.
All right. Yeah. Well, unfortunately, due to the time constraints, there were several parts from the paper that we were not able to include. But the very first part of this was kind of a small study where we position the real object and the virtual on top. If you see the experimental setup, we have them separated. But this first study was basically aligning a virtual object on the same position of the real one, right? And then that helped us to investigate, for example, what was the just noticeable difference between these spaces. So this is how we define 3 different positions for the real and the virtual tumor. So yes, we explored that. I did not mention it because of the time constraints, but if you refer to the paper, then there is a specific section that can answer to that question.
Thank you very much. So I think this is the end of the session. Thank you very much for all our speakers again for all those great presentations. We can now join the Q&A track B of Gatathon to continue this discussion and enjoy the rest of the conference.